the last talk of PSSCMP, and I give the honor of closing this year's summer school to Professor Wassem Bakr from Princeton, who will talk more about topological physics of cold atoms.
Thank you. So thank you for staying here for the last talk. I'll be continuing this pedagogical review of experiments that have been carried out with...
Your microphone. The big one.
This one is on. Is this one on? No? Oh. Is that better?
Yeah.
Okay, good. So I'll continue this pedagogical review of topological physics experiments that have been carried out recently with cold atoms. And here's the outline for today. So you remember last time I showed you a couple of examples of lattices which have a topological band structure that were investigated using atom interferometry in these systems. Today what I'd like to tell you about is a few experiments where we start with a lattice which does not have any topological band structure, but then we introduce topology using Floquet techniques. Okay? So I'll tell you about the realization of Hofstadter models and Haldane models. And then I'll move on. So these experiments, Chern numbers of the bands, of the topological bands are measured with both topological currents. So I'll explain how the technique works. So far I haven't told you at all about edge states. So I'll explain how edge states have been observed in experiments, actually not in real dimensions, but in synthetic dimensions. And then I'll tell you about spin-orbit coupling and current efforts towards using that spin-orbit coupling in combination with strong interactions to realize topological superfluids. Okay, so you remember from last time that the problem we encounter with trying to study topology with cold atoms is that these atoms are neutral. And so gauge fields have to be engineered artificially because we don't have a Lorentz force. So the technique we were trying the approach we were trying to follow was to basically have our particles behave just like charged particles in a magnetic field, where you know that in a magnetic field you pick up an Aharonov-Bohm phase as you go around a closed loop. And here we're trying to do the same thing, have our neutral particles go around a closed loop in real space and pick up a Berry phase. Okay, so the technique we'll use is based on periodic driving. And I hear that Shivaji gave a talk about periodic driving and Floquet theory, but I'll quickly review the main results here. So Floquet theory is a way we can tackle periodic Hamiltonians. And so we're considering a Hamiltonian, which after one time period looks the same, and we're solving the Schrödinger equation with that Hamiltonian. And so we'll draw an analogy with a particle in a periodic potential, where we know the solutions are block states, where you have a wave function. The solution looks like a wave function that's periodic in space, multiplied by an exponential factor, which is e to the minus iqx, where q is the quasi-momentum. Here we have the analogous thing when we have a Hamiltonian periodic in time. You have a function that's periodic in time, but multiplied by an exponential that now instead of the quasi-momentum has the quasi-energy. So the energy is no longer defined just like the quasi-momentum. It's only defined up to modulo the drive frequency. Okay? So in pictures, what this means for a periodic potential, if you have a particle with a parabolic dispersion, in a periodic potential, you start copying those parabolas over, shifted by the reciprocal momentum, and then this would give you, once you open up gaps, this would give you the band structure of a solid. In this case, and of course you can define a first Brion zone, where whose size would be the reciprocal lattice vector. So here with in Floquet theory, what we do is we start with an eigenspectrum. Okay? And once we turn on the periodic drive, we have to copy the spectrum over, shifted along the quasi-energy axis this time. And we shift it by one frequency, drive frequency every time. Okay? So we can again define a first Rowan zone in this Floquet theory, and its size is the drive frequency. Okay, so what I'd like to focus on now is a particular case where we can apply this Floquet theory, and that is the case when the drive frequency is very large compared to the energy span of the spectrum. So if we define delta to be the size and energy of the spectrum, we will work in the high frequency limit such that we can introduce what's known as an effective Hamiltonian. Okay, so the idea of an effective Hamiltonian is now we'd like to introduce a static Hamiltonian that can reproduce the effect of, to some approximation of this periodically driven system. So we can introduce what's known as a Floquet operator, which describes the unitary evolution over one time period, and that's given here. So over one period, you pick up a phase that is the quasi-energy multiplied by the period, and we define our effective Hamiltonians such that you acquire the same phase after one period. Okay, so basically we're reproducing the effect of this unitary evolution with this effective Hamiltonian, except this effective Hamiltonian doesn't have a time dependence anymore. When does it make sense to define this Hamiltonian? It makes sense when the drive frequency is, like I said, much larger than the energy range of the bands under consideration. So basically, in the picture, in the repeated Brion zone scheme that I drew earlier, that's the picture I'd like to look at. Basically, when you copy this spectrum, but they're very far apart because the drive frequency is large. So the quasi-energies in the first Brion zone, they coincide with the effective Hamiltonian spectrum in the high frequency limits. Okay, so let me try to apply this to a simple example that is particularly relevant to what I'll be telling you about, and that is the problem of an atom in a tilted optical potential. So for a condensed matter person, what this would look like is an electron in a lattice that is in an electric field. Okay? But for us, because we have neutral atoms, we don't have, an electric field wouldn't provide an acceleration to an atom. Instead, we can provide the acceleration by tilting the potential, for example, with gravity, or if these atoms have a spin, we can apply a magnetic field gradient, or we could even accelerate the lattice in time to apply the force. So if we put an atom without the tilted potential, you know the eigenfunctions are Bloch states. Now once we introduce the tilt, if the bias between neighboring wells is large compared to the tunneling, then the atom's wave functions are now localized in what's known as Wannier-Stark states. Okay? Because they can't tunnel, there's too much bias between the neighboring sites. So now the idea is, on top of this DC electric field, we will add an additional AC electric field, and we will modulate it. So that is equivalent to basically varying this gradient in time. Okay, so that's what I'd like to do, basically. Okay? And modulate it at a frequency. We can do this Floquet theory at any frequency, but it turns out it's particularly easy to do at a frequency where the modulation matches the bias between neighboring wells. Because once you do that, you can actually now tunnel. The atoms can tunnel, so you basically couple those Wannier-Stark states to extended Bloch states. So I'm not going to go through here's the time-dependent Hamiltonian. I'm not going to go through the derivation of the effective Hamiltonian, but I'll just give you the answer. So basically, the time-dependent Hamiltonian, here we have tunneling between neighboring sites. Here we have a force, a DC force, multiplied by distance. So this is basically the effect of the potential, the tilted potential. And then we modulate the potential here. And we can write an effective Hamiltonian in the high frequency limit, which looks like this. So what you see here is first, the tilt has vanished, because we've bridged the gap between neighboring sites with the modulation frequency. And on top of that, what happened was that the bare tunneling gets renormalized. It gets renormalized it's multiplied by a Bessel function, so it gets a little bit smaller. Actually, these Bessel functions can even go negative. So that means we can switch the sign of the tunneling, and this has been observed in cold atom experiments. You can shake the lattice, and you can switch the sign of the tunneling. But that's not the part I'm interested in today, but rather I'm interested in this phase factor. Okay? So basically, this is the phase of the drive relative to the Bloch oscillation. And so far, it just appears as an innocent phase here. But you can see what's happening here is we get a complex tunneling, which is the first step towards engineering a Berry phase. If we can make this complex tunneling, the phase of this tunneling, spatially dependent, then what we can hope to do is as we tunnel around the plaquette, we can pick up a Berry phase. Okay, so let's try to make it spatially dependent. And the goal here is to obtain a Hamiltonian like this one, which is a Hofstadter model Hamiltonian. So what you have here is two types of tunneling. So that we're on a two-dimensional lattice. The atoms can tunnel along the horizontal direction and along the vertical direction. Along one of these directions, we just have a regular tunneling with a matrix element J. And then along the other direction, we have a complex tunneling. Right? So this comes with a phase, and this phase is spatially dependent. So M and N are the indices of the lattice sites. So in this case, I picked a particular phase in space. So this is just a constant phase along the diagonals of the lattice. All right? And it's multiplied by pi over 2. So this will turn out to give us a Berry phase of pi over 2 per plaquette. So in units of pi over 2 on the plaquette, what this looks like is you have these constant multiples of pi over 2 along the diagonal. So that's the phase of the drive on a particular lattice site. Right? So if I focus, for example, on one of these plaquettes, then the phase of the drive here is pi over 2, pi, 3 pi over 2, pi. And now, if the atom is tunneling along this bond, well, that one would tunnel with this term here along the horizontal direction. So it picks up e to the I pi over 2 phase. Along this vertical, it just goes like a regular tunneling, J. And then this one goes with a complex conjugate of this term, e to the minus I pi, and then another J. All right, so the net phase that you pick up here is minus pi over 2. So if we can engineer this sort of situation where we have complex tunneling along one direction, whose phase is modulated this way, we can engineer a Berry phase as you go around the plaquette. So what are the requirements experimentally? Well, what you'd have to do is apply a tilt, just this tilt I showed you earlier, along the horizontal direction, so to suppress the regular tunneling. And then you would have to arrange for a drive that reestablishes the tunneling, but now with a phase that has this configuration. So what is this phase that you need? How do you get that? Well, what you need is basically a periodic modulation along the diagonals. So one way to get that in a cold atom experiment is to have a running wave, so that that is produced basically by the interference of two laser beams. So the potential on here, for example, is modulated in time at the frequency which corresponds to the tilt between neighboring sites. And the phase of the running wave is then constant along the diagonals. Okay, so that's the idea. These ideas were put out in a theoretical proposal by Yaksh and Zoller in 2003, and they were realized in experiments from the Bloch and Ketterle groups 10 years later. So this is the configuration. You have two laser beams. Those interfere to give you running waves that produce the periodic modulation on the lattice sites. And basically by tuning the angle between the laser beams, you can arrange to have whatever phase distribution phi mn that you want, and therefore you can control the amount of flux per plaquette that you can produce. Okay? So basically this is the periodic drive we'd like to add. A running wave, and the phase is just the difference in the k vectors of the light multiplied by the position which on the lattice would be discretized. So this was how they realized the Hofstadter model. I'll show you I'll tell you later about how they measured properties of this Hofstadter model in a second. Let me tell you about another model that was realized also recently in cold atoms, and that is the Haldane model. So the Haldane model is a model which is on a honeycomb lattice, and you have tunneling between neighboring sites. So the honeycomb lattice has two different sites, A and B, sets of sites, and basically you can add two terms, one which corresponds to breaking the inversion symmetry between the A and B sites. So this difference in the on-site energy. And then on top of that, what Duncan here considered was adding a complex tunneling term. Okay, so that's basically, it's a complex next nearest neighbor tunneling. So hopping along these directions with a complex phase. And the interesting thing about this model is, this is like a graphene lattice. The reason I draw a squished unit cell is just because that's what they realized in the experiment. Due to restrictions of the experiment, they couldn't actually shine the laser beams of the optical lattice to get a proper hexagon. But that doesn't matter at all. The topology is still the same. So the interesting things here, you start out with a band structure that looks like that of graphene. You have Dirac points that have Barry phases of pi and minus pi around each Dirac point. And then if you break the time reversal symmetry by introducing those complex tunnelings, those bands split up and they acquire Chern numbers. And the interesting thing is that the net flux through a unit cell is actually 0. Okay? So here's the effect of introducing the different terms. If you have inversion symmetry and time reversal symmetry, you just have the Dirac points. Okay? In this case, they're inside the Brillouin zone again because of the squishing of the unit cell. If you break the inversion symmetry only, what happens is you basically spill the Barry curvature out of these points. You still go around this one, you pick up pi, around this one minus pi. Now if you break the time reversal symmetry, you again spill the Barry curvature, but in this case both of them have the same sign. And so the band acquires a Chern number. And in Duncan's papers, he shows that this is the phase diagram that you would obtain. You have a Chern number of 0 along this axis, and if you move along the complex tunneling axis, you see a Chern number of 1 or minus 1, and that's the phase diagram they reproduced in the experiment. So what did they measure in both of these experiments? Well, actually, first, before I tell you what they measured, let me tell you how they can realize this Haldane model experimentally. So the idea was inspired actually by proposals from condensed matter, where there were predictions that if you shine circularly polarized light on graphene, you would obtain a topological state. And so it's a very similar idea here. We'd like to somehow introduce these complex tunnelings, and the way to do it, it turns out, is again using Floquet theory. So what you do is you shake the lattice. Okay, so here's the lattice, and you shake it around. Okay, and so this is the set of laser beams, which I told you is kind of a weird configuration of laser beams that you would expect to produce a hexagonal lattice. Usually with a hexagonal lattice, you would expect you want beams along sort of a triangle. You can do that, but unfortunately in their experiment, their vacuum chamber was square, so they couldn't do that. So they had to come up with a different scheme. But the key thing I want to show you here is that they had these mirrors which can basically shake the lattice. You just move the position of the mirror in time with a piezo electric element, and you can move the interference pattern back and forth. And if you modulate those so that they are out of phase by 90 degrees, you can actually take this hexagon and take it in a circle. Okay? So this elliptical driving, if you solve the Floquet theory problem, yeah?
How do you make a Hamiltonian lattice with the like I can see how you make a square lattice, but
Okay, this is rather complicated to explain. So basically they have, I think, so this set of beams, this beam and this beam, produce a square lattice, okay? Because they don't interfere with each other. They have opposite polarizations, this beam and this beam. Or I think they might be opposite in frequency. The other beams do interfere and they produce a pattern. It's going to be hard to draw now. It's sort of diagonal. And when you overlay those two on top of each other with the proper ratios, you can actually get something like a hexagon, but not the hexagonal symmetry. Quite right, okay. This drawing is not telling you much, but that's the main idea of what they did. Okay. Let's see. Okay, so what did they measure in both of these experiments? Well, one approach to measuring the effect of having buried curvature in a band is to use the semi-classical motion of a wave packet within the band. So if you look at the semi-classical motion of atoms in a band that has some buried curvature in it, these are the equations. First equation is pretty simple here, or the second equation. That's just the force is the rate of change of quasi-momentum. The other equation tells us that the velocity is actually has two terms in it. One, which is the usual group velocity, and the other is a contribution that looks like a whole velocity or an anomalous velocity. So basically, it's proportional to the buried curvature, and its direction is orthogonal to the force you apply. So if I plug this rate of change of momentum in here, I get this equation. So you apply the force one way, and the atoms move the orthogonal way. So this is basically the anomalous velocity term that we can try to measure in these experiments. And this was proposed in theory by Nigel Cooper and Price. Okay, so now one interesting thing you could do is you can actually integrate this formula over the whole Brion zone. If you do the integral and you assume a uniformly filled band, then the integral of this velocity gives you the net current, and the integral of the Brion zone of this buried curvature gives you the Chern number. Okay. So in the experiments, for example, from the Bloch group, they started with a Hofstadter model with a flux of pi over 2, so it has 4 bands. They put the atoms in the lowest band, and they uniformly fill the band, and then basically apply the force on the atoms, for example, with the magnetic field gradient, and looked at the shift in the center of mass position of the cloud. And if you basically know how much time you applied the force for, you can extract the velocity, and from that back out the Chern number. So for example, for the Hofstadter model, in that case, they measured 0.995, something very close to 1. Okay. So basically, this is, they're just developing the tools for how to do these experiments. We've now learned how to measure Chern numbers. So one thing, so this is using bulk topological currents, but one interesting thing about topological system is the edge currents. And usually in a condensed matter sample, what you have is these hard edges. And so you have localized electrons in orbits in the center, and the classical picture of skipping orbitals around the edges. But in a cold gas, we don't have a hard edge. We're not holding the atoms in a square box, in a square box, but rather in a box potential, but rather in a harmonic trap usually. And the spatial variation of this harmonic trap, it tends to be very slow compared to, say, the spacing between the lattice sites. So it's hard to go and look for edge states in this system. So a different idea was proposed, which is to look for it in what's known as what they call synthetic dimensions. So basically, we'll say, instead of looking for this in real space, let's introduce a different Hilbert space. How about spin? Spin in cold atoms, as I told you before, is a composite. The atom is a composite object, so the spin can actually be quite high. You have the spin of the protons, the electrons, and neutrons. In some atoms, I think you have about 23 states or so. So it's actually a discrete space that can have quite a bit of, quite a number of sites, or number of states, which I'll identify as sites. I'm going to tell you about experiments that were done, for example, with rubidium, which just has, which is a spin 1 in the ground state. And so there are 3 states, -1, 0, and 1. And we'll basically treat those states as if they were sites on a lattice. Okay? And now the advantage is that these sites are discrete, and at the end, basically, if those were the sites in my system, you have a well-defined edge. This is the last state, and this is the other state here. Okay, so the setup is our favorite setup that we keep using over and over, and that is 2 beams shining on an atom cloud. And the frequency difference between the laser beams is such that it bridges the gap between 2 ground hyperfine states. So that's the delta omega over here. And the atoms would transfer momentum to the cloud because they absorb photons from one and emit into the other. So that the process of absorption and stimulated emission actually leads to a transfer of momentum for this configuration along the x direction. Okay? So if you want to write down a Hamiltonian describing this set of Raman processes, so these are processes where the laser beams are far detuned relative to this state here. You're transferring, you're absorbing and stimulated emitting into a beam and transferring some momentum and flipping your spin state. So if you write down a Hamiltonian, this would look like this. Okay? So the terms here are basically, increases your spin while transferring some momentum. So this is a momentum translation operator. You transfer some momentum to the atoms to the right, for example, or you could lower your spin and transfer momentum to the left with some matrix element, which is the Rabi frequency for the two-photon transition. So if we're now imagining those terms in the Hamiltonian as tunneling terms, because now we are imagining the spin space as sites, well, this is a tunneling term which has a phase associated with it, a spatially dependent phase. So here we go again. We have again a tunneling that is with a complex phase, a spatially dependent complex phase. So let's imagine now we add on top of this Raman configuration also a lattice, an optical lattice, a regular optical lattice along the x direction. So now we have tunneling along the optical lattice, which is the usual tunneling. But then along the synthetic dimension of this spin Hilbert space, we have a tunneling that's complex with a matrix element that's a two-photon Rabi frequency, and it comes with a complex phase so that when you go around the plaquette, you again pick up a Berry phase. Okay? So this is again a Hofstadter model. As a matter of fact, if you go and diagonalize the system with periodic boundary conditions, you get something that's very similar to the Hofstadter butterfly. It looks very similar when you look at it at first glance. But the advantage compared to before is now, although along one direction of this ribbon we have, it's infinite, along the other direction we have a very finite system. Okay? This can go up to 23 sites in some atoms. Here with rubidium we just work with 3. But the advantage is now these finite edges would allow the presence of edge states. So these were ideas that were proposed theoretically and shortly followed by experiments from the Spielman group in NIST, Maryland, and from Massimo Ngusci's group in Italy. And so basically now, if you make this configuration and then start the atom's wave function, let's say along this edge, you can do this simply by optical pumping. If you prepare the atoms in a particular spin state, they're on this edge. And you can prepare them with a well-defined momentum. For example, you can do this with a BEC, which has 0 momentum. So they're prepared with a well-defined momentum and well-defined spin, and then you can observe the evolution of these skipping orbitals in these experiments. So you can basically do time-of-flight experiments, extract the momentum versus time, and hence the position. You can integrate to get the position. And you can do a Stern-Gerlach experiment to measure the spin composition and back out from this the edge states. Okay? And what's interesting already in these experiments is they're doing them with interacting atoms. So they can already, this was done with a dilute gas where the interactions are negligible. But some of these groups are already talking about now adding the interactions to this Hofstadter model. And there's a lot of interesting physics that can come out with non-abelian particles, actually. Okay, so far I've been telling you about just magnetic fields. Now I'd like to switch to spin-orbit coupling, how you can realize that with cold atoms. And so the Hamiltonian you're used to in condensed matter is this one, where you have a kinetic energy for the electrons, and then you have the spin of the electrons coupled to magnetic fields. You have a Zeeman field, which is not dependent on the momentum of the electrons. And then you have Rashba and Dresselhaus terms. And those are basically the symmetric and anti-symmetric dependence on momentum. But now, with a cold atom system, you can actually very easily realize, for example, a symmetric combination. There's a combination of Dresselhaus and Rashba in equal amounts. You can actually realize a lot of, you can realize pure Rashba or pure Dresselhaus, but what I'll explain now is just a one-dimensional spin-orbit coupling that's an equal amount of both. So the configuration is again the one we've used all the time. 2 laser beams on an atom, which for some reason is not showing up in this picture. There's an atom here. And the Raman coupling, because of the frequency difference between those 2 beams, would lead to a flipping of the spin. So this is the same configuration we've been using all along. The only difference is I'm going to work in a different limit of the Rabi frequency. So we will work, in this case, at a low Rabi frequency, at a low coupling between those matrix element between those 2 spin states. So again, when we absorb a photon from one beam and stimulatedly emit into the other, we flip the spin and transfer momentum. So this is the definition of spin-orbit coupling. If your atoms are going one way, they're along a certain direction, they have a certain spin. If they're going the other way, they have the other spin. So basically the eigenspectrum, for example, on resonance is 2 parabolas which are shifted relative to each other by the momentum transferred by the light. And now if you this coupling of the laser would actually flip the spin, so it's like a sigma x term. And this sigma x term would open up a gap between those 2 parabolas. Okay? So the terms you're seeing here is this is a spin-orbit coupling that is due to this momentum transfer while flipping the spin, and that's what shifts the parabolas to the left and the right. And then on top of that, there are 2 magnetic fields, one along the x direction and one along the z direction. The one along the x direction is just the Rabi frequency of the laser. Okay? It just couples the 2 spins. The one along the z direction is due to a 2-photon detuning that we can introduce. So instead of being on the resonance, we can actually now just detune slightly, and those 2 parabolas would shift relative to each other in the vertical direction. So we have control over all these things. With the detuning of the 2-photon transition, we control the z field. With the Rabi frequency, that's the intensity of our laser, we control the coupling between the 2 parabolas, the x field, the transverse field, and with the angle of the laser beams, you can actually control the amount of spin-orbit coupling you have. That's how much the parabolas are shifted relative to each other by controlling how much momentum you transfer from the beams to the atom. Okay. So now this was at 0-photon detuning. The parabolas are at the same level, and there's no crossing because I've turned down the intensity of the light to a very low value. Now I open up a small gap by turning up the intensity of the laser beam, and I get a dispersion that looks like this. Okay, as I increase the intensity, this just keeps going up. So this is now, in the stress state picture, I have a dispersion which the atoms can live in. And in this dispersion, so the difference between what I did last time is simply the amount of laser intensity I used. If I kept going, I can have this become a parabola here. And last time I showed you how by introducing a detuning, you can actually shift this parabola so that you introduce a vector potential. But now we'll work at resonance, and with a small Rabi coupling set, I get this double well in momentum space. So what you see here is that by loading the atoms into such a dispersion, the atoms, so this is the momentum axis, the atoms on the left are mostly in the red spin. The atoms on the right are mostly in the blue spin, and in between they are coherent superposition. So this way we have a one-dimensional spin-orbit coupling. So here's an experiment that I've actually done at MIT in a group of Martin's Berline, where we realized exactly this system with a Fermi gas. We introduced spin-orbit coupling, a one-dimensional spin-orbit coupling on a Fermi gas. And the first thing we did was what you call in condensed matter the sudden approximation. You turn on the spin-orbit coupling suddenly. So we just turn on the Raman beams for a short time. And we start with all the atoms in the up state. So this is a Fermi gas that's spin polarized. This is something really hard to do in condensed matter, but in cold atoms, all you do is just optically pump into one of the hyperfine states. So you can prepare a Fermi gas that's all in one spin, which is the red spin. Okay? And what you're seeing here is a time of flight picture of this gas after some momentum, after some time of flight. So you're seeing a momentum space picture. So you're directly visualizing the Fermi sea of this gas. And now we'll turn on the spin-orbit coupling suddenly by turning on this Raman beam. Okay, so basically what we're doing is we're turning on the gap here suddenly. So if the atoms were in the red parabola, they would get transferred. Some of them would end up in the blue Fermi sea. And what you'll see in the movie that I'll show you in a second is we're just changing what I call the Z magnetic field, this two-photon detuning. Okay. So I turn it on, and some atoms go into the blue Fermi sea, which is transferred, they get transferred some momentum by the laser light. And here's the atoms going from the red Fermi sea to the blue Fermi sea, which we're imaging again in time of flight with spin selective imaging. And it's a one-dimensional stripe because this is a one-dimensional spin-orbit coupling. So this is in a sudden approximation. One could also study the dress states. One could try to map out the dispersion. So this is something in condensed matter you would do with ARPIS, for example, like what Zahid Hassan does here. So here we do the analogous thing. Actually, we do the opposite for technical reasons. We started out with atoms that are loaded into different hyperfine states, not the ones that we have the spin-orbit coupling in. And we just turn on the spin-orbit coupling on states that are empty. We essentially just prepare the eigenenergies, but we don't populate them. And then we can transfer the atoms from the occupied states into this band structure by using a radio frequency pulse. So the splitting between those is just a radio frequency photon. So this radio frequency photon has a very long wave vector, a very long wavelength, so there's no transfer of momentum. So it simply just moves the atoms along the vertical direction without a change in the momentum. And now we can take atoms from here to here. This happens at a particular frequency. And then we can map out the momentum of the transferred atoms in this band with a time of flight expansion. And we can also figure out their spin composition using a spin, say, a Stern-Gerlach experiment or a spin selective imaging. So we can completely reconstruct this band structure this way with a spectroscopy. Get the dispersion and the color of the dispersion, basically how much of each spin component we have. Oops. So this we've done in experiments. Okay. But so far this is just a single particle Hamiltonian. The more interesting thing is what happens when you introduce interactions. And one interesting Hamiltonian to realize here that a lot of people are after is to have the analog of what experiments in condensed matter are doing with a one-dimensional tube on top of say like a topological insulator, on top of a superconductor, so that you induce through proximity some superconductivity in the spin-orbit coupled sample, and the combination of these two things can give you something like a topological superfluid. So the analogous thing for us is we don't need to use a proximity effect or anything like that. We can actually just induce strong attractive interactions in the gas to obtain a superfluid. And then on top of that, we can add the spin-orbit coupling we already have. We can have a transverse field that opens up a gap so that you have the dispersions I showed you earlier. And then you can prepare a spin-polarized gas. You can prepare a gas that is only in one of the helicity states and turn on these interactions. And hopefully what you get at a low enough temperature is a superfluid, a topological superfluid, which would, for example, in the harmonic trap, there are computations from this group, for example, which show that you would have Majorana fermions at some regions of the trap. So the new part here would have to add a superfluidity, which requires strong interactions. So I thought I'd just present a few slides on how we induce these strong interactions in a gas. The tool we have is called a Feshbach resonance. And the idea here is, let's say you have two possible states of the atoms. So this is going to be interactions between atoms in different spin states. So those are two atoms coming in a triplet state, in a triplet configuration. And you can draw their intermolecular potential, which looks like this. Okay, so this is the triplet intermolecular potential. And here's what you have for a singlet state, a much deeper intermolecular potential. Both of these support many bound states. And now what you can do is those two states have different magnetic moments, so you can tune them relative to each other with a large magnetic field in the lab. Okay, so what you can do is you can actually bring into resonance a bound state of this potential so that it's on resonance with the free state of the atoms coming in the other intermolecular potential. And in this resonance process, there's actually a resonance of the scattering length. Okay? So this way you can greatly enhance the S-wave scattering length of two atoms. So the picture here again is shown is we have a crossing of the state of free atoms with a bound molecular state as you tune the magnetic field. And this leads to this divergence of the scattering length. So you can freely tune the scattering length from, say, being weak and attractive, which would lead to, if the interaction is weak compared to the Fermi energy, you would get a BCS type superfluid at low enough temperatures, to crossing over, if you just follow this lower branch of the ovoid level crossing, to crossing over to a molecular state where you have the two spin states of the atoms glued together in a molecule that you can think of as a point boson, and this would condense to give you a Bose-Einstein condensate of molecules. And this was shown in cold atom experiments to be a smooth crossover. So BCS superconductors are smoothly connected to helium-4 if you tune the interactions this way. And so the way this was probed, the superfluidity, was just by stirring the gas and observing the vortex lattices that appear. And you can see here what happens as you tune the magnetic field, which effectively is changing the interaction parameter, 1 over KFA, from being in the BCS regime to the BEC regime. And right at the resonance, you have some strongly interacting soup, that's the unitary Fermi gas. And all across, if you stir the gas, you see a superfluid. And the superfluid actually here has a very high critical temperature that's about 16-17% of the Fermi energy, of the Fermi temperature. So if this was an electronic material, this would be well above room temperature, the critical temperature for this superfluid. So we already have the strong contact interactions that would give us superfluidity, S-wave superfluidity. We have the spin-orbit coupling. So now what's required is to put those two things together. So let's say in the experiment I told you about, we're loading the atoms in one of those spin states. Yeah.
What's the difference between these vortices?
What's the difference in the vortices? I mean, the size of the vortex cores, for example, would be different. I think they get bigger as you go towards the healing length changes. So that's one difference. I mean, the critical temperature at which the vortices would appear, because the critical temperature for the superfluidity would change. So on the BEC side, it's high. Here it's the highest, and then it kind of drops rapidly on the BCS side, because you know that the dependence on the interactions of the critical temperature is exponential. So these vortices would have to happen at a much lower temperature. But otherwise, I mean, they're both Abrikosov lattices of vortices.
In the Feshbach resonance that you were talking about there, when you have this bound state, so this is a bound state of two atoms, right?
Yeah.
And these atoms are kind of emulating the electrons, so that I can think of this bound state.
So that's something you don't have in electronic matter. That's really like a weakly bound state. What you usually have is more pairing in momentum space between atoms that are electrons that are on opposite sides of the Fermi sea, and that's the BCS side. The other side, where they look like point bosons, that's more like, say, if you start with a point boson like helium-4, you get a superfluid.
Then I'm having a hard time to understand like how you are, how by studying the atomic picture, you can say that you can correlate them with this BEC-BCS crossover, because BEC-BCS is like Cooper pairs and Cooper pairs condensing, things like that, right?
Yeah, this is the BEC-BCS crossover. I think it's only been realized in cold atoms.
No, I mean, I'm just trying to think what is the equivalence of the Cooper pair in your experiment?
Oh, it's the BCS side. There's a pairing on the moment between the spin up and the spin down in momentum space. That would be the Cooper pair. That's not a real space pair. That's actually a pairing in real space, in momentum space, if the interactions are very weak compared to the Fermi energy. Okay. All right. So here's what now we're turning on the spin-orbit coupling, and we'll turn on the strong interactions. So the interactions in a cold gas are just contact interactions. So you can only get pairing in a singlet configuration. Okay. So you can only get pairing between blue and red. But now the spin-orbit coupling it produces a band that has a superposition of blue and red at some point. So for example, you can pair this atom with this atom. So now if you put the chemical potential of the Fermi gas here, you get a single Fermi C, but you can still obtain within the single Fermi C pairing, and this would lead to topological superfluidity. So here are some initial experiments that are going in that direction. Those are experiments from the Zhang group in China. And the experiment they did was exactly what I was describing. They started with the atoms in one of the spin states, the red spin state. So I have a Fermi C, all the atoms are in the same spin state. In this case, they're all pointing down. And the atoms, they are in a Fermi C, so they have different momenta. So there are some, let's say one of these atoms in the pair is at momentum P, and the other one is at Q. And since these are fermions, here we have a triplet. This has to be antisymmetric in momentum. So those cannot form a molecule because they're in a triplet state. They have to be in a singlet state to form a Feshbach molecule. So now we turn on the Raman coupling, which we can think of as a momentum-dependent magnetic field coupling to the spin. So here's a Bloch sphere picture of what's happening. You have the two atoms initially pointing down. These are the red arrows. If I didn't have a momentum dependence for this magnetic field, if this wasn't spin-orbit coupling, just a regular magnetic field acting on the atoms, then I draw the magnetic field as this blue arrow, and the red spins rotate about that blue arrow. So here they are. After some time, they've rotated to the yellow positions. But at the end of this quantum evolution, they're still pointing the same way. So they're still in a triplet state. They can't pair. But then if I introduce the spin-orbit coupling, that's a momentum-dependent magnetic field, this spin, they'd have different magnetic fields now. This spin would move this way, the other spin would move somewhere else. So now there's a singlet component that can cause pairing through the Feshbach molecules. So that's what they did in this experiment. They turn on the spin-orbit coupling through the Raman transition. They already have the gas near a Feshbach resonance where there are strong interactions. And if they look at the spectra that they obtain, they see that there's a transition here to the free atom state. That's this blue one. But on top of that, they see an additional transition, which is shifted by some binding energy, and this is a transition to a molecular state. This you wouldn't see if you just turn on microwaves, which would be like a momentum-independent magnetic field. Okay? It's only basically because of the spin-orbit coupling that you can now induce pairing in the gas. So we already see pairing in these experiments, but now the challenge is to get to superfluidity. And for that, you need to cool these pairs to lower temperatures below the critical temperature. And so far, the experiments there are about a factor of 2 above the critical temperature. So let me explain what the challenge to getting colder is. The main challenge is that the Raman coupling beams actually introduce a lot of heating to the gas, and they take it above the critical temperature. Even though we initially start below the critical temperature, when you turn on the Raman beams, there's a lot of spontaneous emission from the beams that leads to heating. And the reason why that's sort of a bit fundamental is that let's imagine we want to flip the spin of an atom from up to down with a Raman coupling, with light. So regularly you think the light couples to the charge of the atom. It can just shake the electron. It can't flip its spin. So how can you flip the spin of an atom with light? Well, to do that, what you have to do is rely on the intrinsic spin-orbit coupling within the atom. So that spin-orbit coupling in the excited state is what leads to the fine structure splitting in this excited state. So if you are to flip the spin of an atom, you basically have to use the light and the spin-orbit coupling of the atom to do the spin flipping. But then what you have to do in that case, you have to be able to resolve this fine structure splitting. So your detuning has to be close compared to the fine structure splitting in order to be able to flip the spin. And what happens is initially we're thinking of this virtual state as having a very small occupation, so there's no spontaneous emission from this virtual state. But now as we tune closer and closer so that we are comparable to the fine structure splitting, there's more virtual occupation and therefore there's more spontaneous emission. And the spontaneous emission adds entropy to the gas and takes it above the critical temperature. So the best atoms for doing spin-orbit coupling are heavy atoms, where the fine structure splitting in the excited state is very large. But then it turns out the interactions are strong in the light. Well, this is not a general rule, but the best superfluid we have is actually in a very light atom. the one with good properties where it lives for a long time is actually in lithium. So those two things so far have been kind of incompatible, and the search is on for atoms which would be able to combine these two things together. So to summarize, what I've told you about today is about how you can introduce topology into non-topological analysis using Floquet techniques and experiments which have realized the Hofstadter model and the Haldane model using Floquet techniques, and how they've measured the Chern numbers using bulk topological currents. Shown you how you can study edge states in synthetic dimensions, and told you how you can study spin-orbit coupling and combine that with interactions to possibly get topological superfluidity. So I've given you over these two lectures and sort of a broad overview of the experiments that are being done in the cold atom field to study topological physics, which just happened mostly over the last few years. Some of the things I haven't talked about are interactions. Well, I showed you a little bit of interactions with the spin-orbit coupling, but now people are excited about, for example, studying interacting Chern insulators in these Hofstadter models, for example. There is a challenge. These Floquet techniques that are being used, they're not quite compatible with interactions because the natural like basically when you have a Floquet, you're shaking a system, its natural temperature will tend to go to infinity. The question is there sort of a metastable regime where the interactions have some sort of metastable ground state and like a fractional quantum Hall state, for example, but they don't before all the heating kicks in. There's already experiments on topological charge pumping, which I haven't had time to talk about. And finally, I've mostly talked about alkali atoms, but there's a lot of other systems that people cool down, and those might be very interesting from the point of view of realizing, for example, Kitaev chains. There you need long-range interactions. So magnetic atoms are one candidate. People have cool things like erbium or dysprosium, which have large magnetic moments, and those no longer just have contact interactions, they also have long-range interactions that can be used for Kitaev models. Dipolar molecules also have long-range interactions. In my lab, for example, we're looking at trying to add a Rydberg component to an atomic gas, and this Rydberg interaction can introduce long-range interactions again. So thank you very much.
How do you get around this heating problem that you referred to in order to prepare all of the atoms in, say, a single Floquet band?
Okay, so they're able to prepare it for a single Floquet band, but actually during the measurement, they do occupy other bands. And if you occupy, say, all 4 bands of the Hofstadter model, you would end up integrating over all of them and it would be 0. So they have to take into account, they watch it over time, the system, and they measure the populations in the different bands, which can be done using a band mapping technique. You can map out how many atoms are in each band. And so you can sort of then, taking into account the populations of the different bands, you can back out the Chern number. But it's not as simple as what I presented, yeah. And the problem is the heating from the Floquet, from the fact that you're shaking the system. Yeah.
Your previous talk, you said you're going to give an example of a system which has opposite vorticity. So which system?
Oh, the Hofstadter model, I haven't had a chance to talk about it, but so I showed you how you can arrange the phases, say by applying a gradient, where that leads to a uniform flux through each plaquette, and so it's like a uniform magnetic field. That same Hofstadter model, actually the first realization from the block group was not a uniform field. What they did was use a superlattice, and in a superlattice, basically the gradient goes up one way and then down the other way. Okay, and so when you shake that system, you actually get fluxes that go one way and then the other way, so you get exactly what you want for your model.
More questions? Okay, then 1 second. Okay, so I have a good one.
Okay. As we all know, cold atoms suffers from one crucial limitation, which is that it's impossible to carry out experiments in the summer because the atoms are no longer cold. So we have finally found the perfect solution to this dilemma, which is the Arctic helicrane, which will allow Professor Bakr to transport his entire experimental apparatus to the Arctic and carry out this work year-round.
Professor Bakr, we've done that.
So before we close, I want to thank two administrators who helped us organize everything. So this is Sunu Arya and Sergio Aqua, who did everything relating to housing, registration, and food. Are they here? Are you here? Okay, well, I'd like to thank them. And also Katie and Allison and Michelle and Susan. So they were sitting at the desks and they were doing the food. And they're from IAS, except for Susan, who's also at Princeton, so they also helped, so let's thank them. I think that's it. So Professor Notby, who's the organizer for the second week, the PITP week at IAS, maybe you'd like to make some announcement.
So, is this on?